All right, let's talk about one of the most important skills for your GCSE maths, accuracy. Honestly, this stuff is what can turn a good answer into a perfect one. We're going to build your entire accuracy toolkit right here, right now.
So let's start with the question. Is 499 really the same as 5? I mean, in a shop, you basically treat it as the same, right? But in a maths exam, oh, it's a completely different world. Let's dig into why this tiny little difference is so important for grabbing those top marks.
So here's the game plan for today. We're going to build your accuracy toolkit piece by piece. First up, we'll nail down the absolute core tool, which is rounding. Then we'll put that to work with some smart estimation. After that, we'll get a bit more advanced and look at error intervals, and then wrap it all up with some real-world rounding rules. Let's get into it. Okay, Section 1, rounding. You have to think of this as the absolute foundation for everything else we're going to talk about. If you can master this, all the other skills will just click right into place. The great thing about rounding is that it's just a simple, 4-step recipe every single time. First, you find your key digit. That's the one in the place value the question's asking about. Second, you just look at the digit right next to it, its neighbor. Now step 3 is the big decision. If that neighbor is 5 or more, your key digit gets rounded up. And step 4, if the neighbor is 4 or less, your key digit just stays the same. That's it. It's a rule that works every single time. Let's put that process into action. We need to round this number to 2 decimal places. Okay, so our key digit, the second one after the decimal point, is the 9. And its neighbor, the one that makes the decision for us, is the 5. So, what happens next?
And the answer is 0.30. Since that neighbor was a 5, our rule says we have to round up. Now, when you round up a 9, it becomes 10. So you write a 0 and carry the 1 over to the 2, which becomes a 3. And here's the crucial part. That final 0 is not optional. You absolutely have to write it to show that you've correctly rounded to 2 decimal places.
Now, your exam will throw 2 main types of rounding at you, decimal places and significant figures. They sound similar, but they're different beasts. Decimal places is easy. It's just about a fixed position after the dot. Significant figures, though, is about the most important digits in the whole number, no matter where they are. So, rounding 1,267 to 3 significant figures gives you 1,270. That 0 on the end is a super important placeholder. Getting this difference is key.
All right, let's try a trickier one. We're going to round 3.997 to 3 significant figures. So our first significant figure is the 3, the second is the first 9, and our key digit, the third one, is that second 9. Its neighbor, the 7, is our decider, and I think you can probably see a bit of a chain reaction about to happen here.
And there's that chain reaction. The 7 tells the second 9 to round up to 10, so we put a 0 and carry the 1. That turns the first 9 into a 10 as well. So another 0, and we carry another 1 over to the 3, which finally becomes a 4. So our answer is 4.00. And again, look at those zeros. They are absolutely essential. They are the only way to prove you've rounded to 3 significant figures.
Okay, time for the second tool in our kit, smart estimation. This is where rounding stops being just a rule and becomes a seriously powerful strategy, especially when you're in an exam and the clock is ticking.
So why do we even bother with estimation? Think of it as your secret weapon for checking your own work. It lets you get a quick, ballpark figure so you can tell if your super detailed calculation looks about right. It's fantastic for spotting a silly mistake early on before it costs you a bunch of marks.
Imagine you see this calculation on a non-calculator paper. I mean, it just looks horrible, right? Slow, messy, and easy to make a mistake. But what if we don't need the exact answer? What if we just need a good guess?
Well, here's the trick. You just round every number to 1 significant figure. So 17.3 becomes 20, 3.81 becomes 4, and 11.5 becomes 10. And just like that, this monster of a problem turns into something you can do in your head.
And there it is. 20 times 4 is 80, divided by 10 is 8. Simple. Now we have a benchmark. The real, precise answer should be somewhere close to 8. So if you do the long calculation and get an answer like 80 or 0.8, you'll know instantly that something's gone wrong.
We can even get a bit more clever. Was our estimate too high or too low? Well, let's think about the fraction. On the top, the numerator, we rounded up. On the bottom, the denominator, we rounded down. So we made the top number bigger and the bottom number smaller. Both of those things are going to make the final answer bigger.
So this is an overestimate. The real answer will be a little bit less than 8.
Right, on to our third tool, and we're definitely getting into the more advanced stuff now. Error intervals. This is all about looking at a rounded number and understanding the hidden range of possibilities behind it.
So what on earth is an error interval? It's actually pretty simple. It's just the range of all the possible values that a number could have been before someone came along and rounded it. It's like the zone of uncertainty that rounding creates.
Let's use an example to make this real. Imagine you're told a road's length is 3.6 kilometers, and that's correct to 1 decimal place. But what could its actual, totally precise length have been before it was rounded?
Let's figure out the boundaries. What's the smallest number that rounds up to 3.6? Well, that would be 3.55. And what's the cutoff point at the top end? It's 3.65, because at that exact point, you'd start rounding up to 3.7. So the true length, which we're calling L, is trapped. It has to be greater than or equal to 3.55, but strictly less than 3.65.
And for our final tool, we're looking at something called real-world rounding. This is so important because sometimes the story behind the numbers completely changes the rules of the game.
Check out these two scenarios. First, a school trip. The calculation says you need 3.1 adults, but you can't have 0.1 of a person, and 3 adults isn't enough, so you have to round up to 4 to make sure everyone is supervised. Now scenario 2, apples. The math says you can fill 4.16 crates. Well, you don't have enough apples to fill that 5th crate, so you have to round down to 4 full crates. See? The context, not the number, tells you whether to round up or down.
And there we have it. Your accuracy toolkit is now complete. We've locked down rounding as our core skill. We've seen how to use estimation to check our work, and we've taken an expert look at error intervals to understand what rounded numbers are really telling us.
So I'll leave you with this thought. Now that you know these rules, now that you can see that hidden range of values behind a single rounded number, just how much uncertainty is hiding in the numbers you see every single day, in the news, in statistics, everywhere. Makes you think, doesn't it?